Okay, welcome. So we will start today's second course on the Gadgetron online class. So the outline. We will discuss today about two independent projects, so the magnetic resonance data format, which aim to convert all CAS space from different value to a same common format. And also the second project is the Gadgetron. So as briefly mentioned last week, the outline of the class is really technical. It's not application oriented. So we want to describe the detail that may help you during your research, but in order to use the Gadgetron and the MRD format, but we won't speak a lot about MRI acquisition, MRI reconstruction. This is really a technical speech. So today, Maxime from Bordeaux will first introduce the magnetic resonance data format. So he will use MATLAB for playing with some CAS-based data. And then Vinay from NIH in the second talk will present how you can convert the CAS-based data from Siemens, GE, Bruker vendor to the common MRD format. So what are the steps and in order to retrieve any specific detail from any vendor. Then we will do a small break and we will continue with Rui from the NIH that will explain how to communicate between the scanner from Siemens and the Gadgetron. So we will introduce let's say an add-on or a plugin called ICE Gadgetron that allow bilateral communication. And to conclude the day, we'll have a Q&A session where we'll have the opportunity to speak about the roadmap to use Gadgetron on any scanner and also to ask any question related to Gadgetron. I think I won't describe today how we're going to work, but basically if you have any question, please write on Slack and we will use them and try to answer as soon as possible. I will say just again, try for next week to have MATLAB and Gadgetron and Gadgetron MATLAB installed on your computer because we will use a lot MATLAB for the next course. So I thank you for your attention and I will give back the screen to Maxime.
So today we'll speak about the MRD format, which is a necessary step for unified MR reconstruction with the Gadgetron. So as you all know, nowadays all MR vendors have their own private reconstruction pipeline. So depending if it's Bruker, Siemens or GE. And due to the rise of complex MR processing, such as parallel receive, compressed sensing, SMS, all of that, that might induce some variability across the reconstruction, the vendor-specific reconstruction. And then the question is, even if we have the same data, do we get the same image after this vendor-specific reconstruction? And that's why we wanted to use a vendor-agnostic reconstruction provided by the Gadgetron frameworks. And for that, we needed a unified open source and adaptive frameworks, which allow to increase the reproducibility of the MR processing and also avoid the black box reconstruction, and then increase the reproducibility of MR research and reconstruction. However, a prerequisite for unified magnetic resonance reconstruction is a common raw data format, and the Gadgetron uses the ISMRM raw data format, which we'll call a MRD in all the rest of the presentation. Basically, the main idea is to take the vendor-specific raw data, convert them to MRD, just after the acquisition, avoiding any treatment by the vendors. And then this MRD format is used for the Gadgetron reconstruction to obtain the image. So currently, several converters already exist for various MRI vendors, such as Bruker, Siemens, GE, and maybe Philips. I'm not sure about this one. Okay, now let's talk about the MRD format essence. So basically, these formats need to allow to store the raw case space data in acquisition order, just after the acquisition, before any vendor-specific transformation. We will also need to store the physics parameter of the data acquisition process, because all of these parameters will be required for the image reconstruction. Basically, it's the recipe of the image reconstruction. And optionally, we can also store the trajectory data or additional waveform, which can also be used for the reconstruction. Yeah, okay, sorry for the delay. Okay, so basically, we know that in MR acquisition, the most simple unit is the readout. And in Cartesian, it's just a line, like this. In radial, it's also a line, and in spiral, well, you have a more complex pattern. And the MRD format will capture this unit to avoid any vendor-specific operation. And we will directly store this unit into the data sample here, which we also call a data chunk. For multiple coil acquisition, the signal of each coil is saved. And also, so as we have a lot of this data sample, each of these data item will be preceded by a fixed size data header, which includes some information such as the data type, some acquisition flags, and some encoding numbers. And those numbers will be used basically to place the data sample in the case space or outside of it if the data is not part of the image sampled, because the data chunk can also include a navigator or calibration readout data. So basically, MRD dataset also contain a flexible XML headers in which we can have an arbitrary number of fields to accommodate all the parameters which we might need for an experiment and not for others. So we have all the dataset parameters such as the field of view, the matrix size, but we can also have the b-value if it's diffusion experiment. All of that goes into the XML headers. So to summarize, we can say that an MRD dataset is an XML general headers with the dataset parameter plus n times one data header here, which includes some encoding numbers, and some data sample here, which include readout times coil data. And the MRD format can also support additional waveform, such as the ECG, which can be used in a cardiac MRI for the reconstruction of cine imaging. It also includes contours and landmark, making it suitable for AI research, and that's why it has been used in the FAST MRI project. So the Gadgetron also used the MRD format to store the images after the reconstruction. So here, and here you have both the image and a small image header, which is used if you need to send back the image to the scanner and then display it with the correct FOV and the correct orientation. In this header, you can also store some user-specific parameters, such as the b-value for a diffusion experiment. So I know that a lot of you might be more used to a DICOM or NIFTY format, and this kind of conversion needs to be performed by the client. So I think we have a MRD to NIFTY converter, which is in a beta test for now. And there is also a DICOM writer, which is a part of the Gadgetron. So you can get both at the end. The MRD used the hierarchical data format, HDF5. The extension of the file is .h5. And it was originally created to store a very big amount of data. So that's nice because you're not limited basically in the number of data you can save. It was created in 1987 by the National Center of Supercomputing Application. Now it's maintained by the HDF groups, and it's open source, it's fast, and it's widely used in the research community. It's also used by the NASA, so it must be nice. Okay, now let's talk about the MRD library and tools. So the ISMR-MRD library provides a C++, Python, and MATLAB interface for reading and writing the MRD file. This library can be compiled on Linux, Windows, Apple computer, as described on this link, but it's also included in the pre-compiled packages which you already installed. So no rush on your terminal with those commands. You already have them. So everything should be done. Okay, so to have a look to it, let's create a ship Logan Phantom with the Gadgetron. So for that, well, we've seen that in the Christopher presentation. You just need to open a terminal and shout his name into the dark void. So Gadgetron here. And then you can use the command ISMRM generate ship Logan. Oh, I need to remove it before. So it's going to go here. Okay, and we want it in English. Okay, great. So here you can create your Cartesian ship Logan Phantom. We can have a look in the folder here. Should have something which is called testdata.h5, which we just created. And we can use the ISMR-MRD viewer to look at it. So yeah, it's here. So here we can come back for that to the slice. Here you have two possibilities to install the ISMR-MRD viewer. One is direct, and the second one is through a virtual Python environment. I would suggest to use the one which works. So for me, it was the virtual Python environment. And then I can launch it like this. Okay. Up, so it's here. Okay. And now we can open the file. Okay. So here you see that you have the header of the file with some information, such as the number of receiver channel, the institution name, and you can also have a look to the acquisition, to the readout, which are stored, which are here. And you can see that here you have the information of the small data header. So here you can see you have the encode step 1, 2, 3. And if we go to the 128, it should be nicer. Okay, you see your echo data. Okay, another way to have a look to this data is through MATLAB. So basically, here, okay. So basically, in the next example, I will put some code into MATLAB to have a look to the dataset. If you have MATLAB, well, feel free to do it with me. And if you don't have MATLAB, you can just scroll on the slide. I will try to, which you have on the GitHub, and you should see all of the results and all of the code which I use. So for now, let's go to MATLAB and try the first lines. So here we just add to the path the ISMRM library, and then we just try to load the file. Yep. Like this. Okay. So we see that we use the ISMRM dataset to create the dataset ID object. And then from this one, we can have the header with the ISMRM XML deserialize function and the data structure. So if we go in the data structure here, we can have a look to our data, and we see that there is 256 cells. So that means 256 data chunk. And in all of these cells, we have a matrix of 512 readout points times 8 coils. Here we can also have the trajectory. Here it's empty because it's only optional. And on the head part, you have all the information about each of the data chunk. And that's why, as an example, you have the slice direction here, and you have a 3 value and times 256, which is the number of data chunk. Something which is also very nice here is the IDX structure, in which you have the K-space encode, step 1, step 2, and the number of average, slices, contrast, phase, repetition, all of this. And also some user parameters. Okay. We can also have a look to the main header of the data here. And here you see the field that we've seen with the ISMRM viewer. You have the version, you have the acquisition system, so the number of received channel, the institution name, all of this. Then you also have in encoding the encode and recon space with the field of view. And this doesn't change, so it's in the main XML header. So we can now just make a loop to create our K-space. So for those which look at the slices, we are now here. Yep. So we can use this command, and here we'll create the K-space matrix with 512 readout point, 256 data chunks of phase and code here, and 8 coils. And here we can directly display this matrix, and we get the images of the K-space acquired by each coils. We can just perform a very basic reconstruction by doing a 2D Fourier transform and get the image of each coil. And then we can plot those images. Okay. So I hope I'm not too fast. All of the code which I used, it's included into the slide, which you can download on the GitHub. So feel free to download it and then copy and paste. So of course, we can also perform this reconstruction using the Gadgetron. So for this, we need one running instance of the Gadgetron. And we also need to use this line to perform a basic reconstruction. So here I have my running Gadgetron, and I can here perform the reconstruction. We see that the Gadgetron is active here. It worked and finished. And then we can go back to ESMR MRD viewer. And open the result of the file. And here it's the out.h file, which we open, and we get the image reconstructed by the Gadgetron. Okay. So this is also something that we can do on MATLAB with the following command. So I'll show you, which you can copy and paste. So we first clear everything. So here you see that we used the HDF5 info and then the HDF5 read, which are some functions provided by MATLAB to open this kind of data set. And with this, we are able to retrieve the image, which we have here, which I can plot it like this, like that. So it's our ship Logan Phantom. And we also have the header, image header, with some field, which is, and some of them are very important if you want to resend the reconstructed image to your scanner. So that's why it's especially important to have this header. It also provides you some information which allow you to plot it well with the good field of view and everything. Okay, now let's go back here. Okay. So now we'll do a second exercise on a more complex dataset, which is a 2D multi-slice EPI dataset. But basically, we'll do the same thing to have a nice reconstruction, and we'll have a more detailed look into the function that we used. So here it's the same. If you have MATLAB installed, you can follow the exercise with me on MATLAB, either on a live script on MRD API reconstruction.mlx, or if a live script doesn't work, you also have the MRD API reconstruction.m. And if you don't have MATLAB, you can just follow the slide, and in which everything is displayed as well. Okay, so let's go for the first step. I will just clean it. So we'll open the FID, which was shared with you on the Xenobo, which is called FID EP2D SE no iPad 3 slices.h5. So you have to put it in a defined dataset path and fill the path here. Yep. Then we'll use, okay, let's do it. Okay, perfect. So now we use the dset to create the ISMR, the dataset ID, and then we retrieve the main header here with ismrm.xml.deserialized. And we also retrieve the data structure with dset read acquisition. And here we can have a look to both the data structure, the data structure in which we have 393 cells, and this is the number of data chunk. So for that, advance, we can compute here the number of data chunk just by looking at the size of the data struct matrix. Here it's 393. In EPI, we expect this data chunk to come from each phase encode, so blips, of each slices. So basically, if we want to compute how many we should have, we can just compute the number of blips of phase encode in the API dimension and the number of slices. So let's do that. And here we see that we have 128 phase encode and 3 slices. This gives us a number of 384 data chunk that we expect. That means that we have 9 additional data chunk in our data. So those data chunk could come from 3D encode, come from some average, repetition, contrast. So we can have a look to those values. And to have a look to those values, we are going to go to the header, encoding, encoding limit, and the case space encoding step 2 for 3D encode. So I can do it like this, header, encoding, encoding limits, and we have here case space encoding 2. And we see that here the number are 0 because they start from 0. So if you want, so if we run that, then we can have their number. And here we see that we have 0 or 1 if we want in all of those, which means that our additional data chunk did not come from a 3D encode, average, or contrast, which makes sense because we have only 9 of them. And if we would have a 3D phase encode, then we would have a multiplication factor of them. So the next possibility is to have a look to the flags of the data. And for that, we go to the data structure, then the head, then flag is set with the name of the flag. We can have a look first to the list of the flag, head, and then flags. And here we have flags for everything, basically. So ACQ, first in encode step. I mean, all is in the name. So if you are looking for a defined flags, you can have a look here, and then use this line with the name of the flag to get its value. So let's do it. We do that. So here we got the flags, and we can do the sum of the flags and get the number of parallel calibration. Here it's 0. The number of navigation data, it's also 0. And here the number of phase correction data. And here we find our 9 additional data chunk. So they are used for phase correction data. Basically, it's 3 readouts in the opposite direction. Okay. And they are used in EPI for a ghost correction. So the next step is to sort our image data to remove those readouts, which doesn't come from the images. And we'll do that with just finding which data are not parallel calibration or navigation data or phase correction data. And now that we have this, we can create a matrix of the image readout. So we can prepare the matrix with the number of the readout size, the number of coils, and create this blank case space matrix, and then just do it with a loop. Okay, now we have our case space matrix, and its dimension is 256 points, which is the length of a readout, 128, which is the number of phase encode, then 26, which is the number of coil, and 3, the number of slices. Of course, you have all of these parameters also here. So as you know, in EPI, the odd and even echoes are acquired in opposite direction, which means that some of them are reversed. And to get rid of that, we can have a look to the ACQ is reversed flag, which is here. Just by doing this, we have now the ACQ is reversed flag here. I will open it here. And we see that 1/2 readout is reversed. And to get the nice EPI matrix, we can just flip 1 readout over 2, and then do a very simple and direct reconstruction by performing a 2D FFT. So let's do it. Yep. Okay, and we have here our image no regrid, like that. We also know that usually Siemens use, and those are Siemens data, they use oversampling to avoid folding in the readout dimension. So we need to remove this oversampling before image display to have the nice image. And we can just check that by comparing the size of the matrix, which is for now 256. And if we go to the header, encoding, encoded space, matrix size here, we see that the number of encoding was just 128. So we have a factor of 2, which means that we have an oversampling of 2. And we can just remove it to the image no regrid by a cropping operation. Okay. And from this, we can plot our 3 EPI slices. So we can see that the reconstruction work in a way that we really have 3 different slices, but it's not very nice because we have a lot of ghosts here and there on the edges of the image. And that makes sense because in EPI here we acquired the readout during the whole gradient shape. And this includes the gradient ramp. That means that we need to take into account this ramping, this non-uniform K-space acquisition to have a better reconstruction. So this is an excellent example because the parameter of this gradient ramp are stored as user parameter, which means that there are parameters that you can easily like set especially for a reconstruction. So let's have a look to them. So it's inside the header here, and then it's wait, it was there. It's header, encoding, trajectory description. Yep. Encoding, trajectory description. And here we have our user parameter long. And here we see that we have the ramp up time, the ramp down time, the flat top time, and the acquisition delay, which will be used to create basically the shape of the gradient ramp, the theoretical one, and then correct our data with this theoretical ramp. So as there is a lot of dots in this field name, I prefer to use those loops to store those parameters into a more simple structure, which here I called parameters. So let's do that. Okay, and now we have our parameters structure here with all of the information which can be interesting for a more advanced EPI reconstruction. So, and the more important being the ramp up time, the ramp down time, the ACQ delay time up here, the number of samples, but also the field of view, and of course, the ACQ is a reverse flag because some of readout need to be reversed. Okay, now I'm nice. So I prepared a function which will do all the work on the K-space to have it corrected with this API trapezoid regrading. And you should have this code as well if you download the dataset. This code also do a 1D Fourier transform in the readout direction and also remove the oversampling. So after that, what we just need to do is a Fourier transform in the second dimension with the FFT K-space to X-space function, which you should also have. And then we can just do a sum of the absolute value of the image and plot the three slices. Let's see how it goes. Yeah. Here are our images. They are much nicer than the previous one, but you can still see the ghost artifact here and there. And this artifact could be almost perfectly removed by using the 9 readout that we discard at first, the 9 phase correction data. So I didn't code this part because it's quite complicated. But if you want to do it now, I'm sure that you won't have any troubles to find the parameters or anything about it. Now, okay, we can go back to the slide. Yep. And I will even do something very nice. Yep. Yeah. So I'm sure that now you already seen during the presentation that we have a main header, which we open with the shape, the gradient shape parameter, with the field of view, with all of that. And that sometimes we also use the flag, which are in the data header, to look at the data which were calibration data, to identify them and to place them in or outside of the matrix. And that's why we used this architecture. So as a conclusion, so if you've done all of this, and so to conclude, I want to say that the MRD dataset is a versatile format for storing raw MR data and the associated parameter required for reconstruction. It supports a very large dataset, and I think that's why it has been chosen the first time. And that's the HDF file format might not be the easiest to use at first, but then you will see that you have easy interfacing with any language such as C++, Python, or MATLAB, as I've shown you today. And moreover, you have the ISMRMD library, which provide tools for opening or viewing a MRD dataset. So that's it for me. I hope you succeed to follow the script. I hope I wasn't too fast. If you have any question, it's the time for it.
I think there may be some problem for people unmuting, but there is a question on the chat. Is trapezoidal regridding implemented in the
I see a question on the chat. The question is trapezoidal regridding implemented in the Gadgetron? And the answer is yes. So there is already a reconstruction which is provided for the API data, which include both this regridding, but also the ghost correction based on the phase correction data, which we remove on this simple example of API reconstruction. So yes, there is all of that. It also includes pre-whitening and all of this nice gadget. Any additional question?
Can you hear me?
I can hear you, Oliver.
Okay, otherwise I will give back the mic and the screen.
Okay, thanks, Maxime. Not sure if Vinay is ready for the next talk. I will just brief a few things. So if you want to start a project with the Gadgetron, it's really a good idea to just have a look offline at the car-space data, either in MATLAB or with the MRD viewer. Like that, you can see the kind of data you're facing. So it's important to check if you're having some navigation data and or only car space, if your car space is fully encoded. And once you're familiar with the format, it will be really easier, for instance, to exchange with us, and because we use it a lot. And you have exactly the same way of looking at the car space data. So you can obviously use some vendor conversion. So like there's a package like VBVD for Siemens, something like that, I guess. And but once you use the MRD format, it will be more easy to put your reconstruction than after in the Gadgetron. So we can come back to how to do it or how to start a project with a specific sequence in the QA session, and I think everybody will be happy to answer.